Welcome to this deep dive into the anatomy of a Recoater crash in laser powder bed fusion. Today we will explore why these crashes happen, the lasting consequences they leave on materials, and the advanced modeling techniques we use to prevent them from occurring in the first place. While we are getting started, go ahead and subscribe to the channel so you can stay at the forefront of additive manufacturing. A Recoater crash isn't just a random accident, it is a deterministic event driven by a part's thermal history. When vertical distortion in the Z direction exceeds the layer clearance, typically between 20 and 50 microns, the part enters the interference zone. Any superelevation beyond a 15 micron threshold leads to solid clipping, where the Recoater blade physically strikes the part. The root cause of this distortion is heat accumulation, especially in unsupported features. As you can see in these charts, features without supports reach the critical 40 micron deformation zone very quickly due to rapid vertical expansion. However, when we treat supports as thermal conduits, rather than just structural anchors, they stabilize the geometry by dissipating heat into the base plate. The type of Recoater blade used determines how catastrophic a crash will be. Hard blades made of steel or ceramic are unyielding. A collision here is often catastrophic, causing the machine to stop to prevent damage. Soft blades made of silicone or rubber will yield to the protrusion. While this prevents a machine jam, it creates a silent failure, where the build continues, but with significant internal defects. With soft blades, we face the challenge of porosity generation. As the flexible lip bends over a super-elevated feature, it leaves excess powder in its shadow. This creates a locally thicker layer that the laser cannot fully penetrate. This leads to incomplete melting and results in lack of fusion porosity and internal voids within the final part. We can identify these crashes in real time using in-situ vibration monitoring. By tracking acceleration spikes, we can distinguish between normal powder drag and a crash. An interference greater than 15 microns generates distinct clipping signals, providing a clear diagnostic signature of a mechanical interaction. Visual evidence on the powder bed, such as streaking and debris drag, confirms these interactions. While soft blades might leave minor vertical streaks, hard blade collisions cause significant material propagation across the plate. A single crash site can actually compromise neighboring parts by dragging solid debris into their build paths. The most dangerous aspect of a Recoater crash is its impact on mechanical properties. While yield strength and hardness often remain unchanged, there is a critical loss of ductility. Elongation at break can drop to a mere 1 to 3%. This means parts may seem fine under static loads, but will fail catastrophically in fatigue or high-strain applications due to internal notch effects. Internal porosity isn't distributed evenly, it is highly sensitive to part orientation. Walls oriented 90 degrees to the Recoater travel direction suffer the most vibration and bending. This results in the highest defect density, with some clusters showing up to a 28.5% coefficient of variation in porosity. To prevent these issues, we need simulation. However, standard finite element analysis, FEA, is often too computationally expensive for full plate production, taking over 25 minutes per part. We need a faster way to identify these risks during the design phase. That solution is the graph theory approach. This method is 5 to 6 times faster than non-proprietary FEA, while remaining accurate to within 4 microns of ground truth. In our validation tests, graph theory predicted a crash at exactly layer 548, matching our experimental results perfectly. Our first line of defense is a paradigm shift in geometric design. We must design supports not just for gravity, but for thermal mass. By increasing the conductive pathway, we can keep Z deformation below the safe limit of 15 microns, effectively neutralizing the risk of superelevation. We can also use DynamicPrint and Feedforward modulation. By adjusting laser power and velocity layer by layer based on thermal simulations, we can maintain a constant thermal history. This approach has demonstrated a 45% reduction in support volume, while completely eliminating distortion defects in complex aerospace components. In conclusion, moving towards zero-defect manufacturing requires a 4-step protocol: predict using graph theory, mitigate through thermal support design, monitor via vibration signals, and assess the ductility of parts in known crash zones. This comprehensive approach ensures reliability in every build. Thank you for watching our technical analysis of Recoater crash mechanics and their impact on part integrity. Mastering these thermal pathologies and following the diagnostic protocols we've discussed is the essential first step toward achieving zero defect manufacturing. If you found this deep dive valuable, please subscribe to our channel for more advanced engineering insights. Your support allows us to continue sharing the research that keeps your builds safe and your mechanical properties reliable. Hit the notification bell, and we'll see you in the next deep dive.